Welcome to my channel, the number one channel for structural insight. Today I want to tackle example number 1, and this is continuous beam L and T beam designed to BS 8110. So the question is on the board and it reads, a typical floor plan of a small building structure is shown below. Design continuous beam 3AD and B15, assuming slab supports an imposed load of 4 kN per meter square and finishes of 1.5 kN per meter square. The overall size of the beam and slab are indicated on the drawing. The column are 400 by 400 millimeter. Take FCU to be 35 Newton per millimeter square, Fy for 60 Newton per millimeter square, and the cover to all reinforcement is equal to 30 millimeter. So this is the section of the beam. So this is a T-beam. It has an effective flange of 3750, and this is the depth of the slab, which is 150 millimeter, and this is the depth of the beam, which is 400 millimeter. So let's see how we can tackle such a question. So this is the floor plan. As you can see, this is the floor plan, floor slab plan. So this is the arrangement of column, as you can see, and then the wall. So we have been told to design a continuous beam 3AD. So this is 3A. So this is 3, and then A. So it is this beam. (3AD). So it is this beam. So let's continue. Also, I want to clean here so that you can get more space for more calculation. So solution, the first thing to do is to calculate the loading. So solution, so we have the loading, and loading, we have the dead load, which is Gk, and we also have imposed load, which is Qk, like that. So we will start by dead load. So the dead load will be the weight of slab which is given by the area of the cross section times the density or the unit weight of the concrete. So we will assume a unit weight of concrete to be 24. So this one is equal to, it will be this, it will be the area of this slab alone. So that one is equal to this distance from here to here, that 750, you divide by 1000, you'll get 3.750 times the thickness of the slab, 150 divided by 1000, 0.15 times 24, which is the unit weight of concrete. So this one is equal to 13.5 kilonewton per meter. And then we proceed to weight of downstand. Weight of downstand. So this is the weight of this, of the downstand alone, this one. So remember, this was the weight of the slab alone, which is 13.5 kilonewton per meter. So the weight of the downstand is equal to the area of this downstand, which is 0.3. We have converted 300 to meter times 0.4 times 24. Again, we have converted 400 millimeter to meter. So this one is equal to 2.88 kilonewton per meter. So remember, I said that a T-beam, it will support half of this and half of this. So this beam is supporting a half of this slab and a half of this slab. So it is supporting a half of 3.75 and a half of 3.75. So which will make up to 3750 if you add a half of 3.75 plus again a half of 3.75. So this is a section cut across this beam. So this is what you will see. So this 550 times 300 is the dimension of this section. As you can see, 550 is the h, is the overall height, which is 150 plus 400. And then 300 is the width of the beam. So let's continue. So after calculating the weight of the slab and the downstand, what follows next is the weight of the finishes. So the weight of the finishes. So finishes is equal to, we have already been told in our question, let me check in the question. So the imposed load of the finishes is 1.5 kilonewton per meter square. So 1.5 times the effective length, which is 3.750. So you will get, so the answer is 5.625. 5.265. This is kilonewton per meter. So that is all about the dead load. So we will get the total of the dead load, which is equal to the weight of slab plus weight of downstand plus weight of finishes. So you will get 22.0 kilonewton per meter. So which is GK. GK is equal to 22.0 kilonewton per meter, like that. Then we proceed to imposed load. So imposed which is QK, is equal to, in the question, we were given 4 kilonewton per meter square as an imposed load. So this one is equal to 4 times the width of the flange, or no, the effective flange, which is 3.75. So this one is equal to 15 kilonewton per meter. 15 kilonewton per meter. So that is the imposed load. So what follows next is the ultimate design load. So the ultimate design load is equal to 1.4 GK plus 1.6 QK. So GK is the dead load. So this one is equal to 1.4 GK, which is 22.0 plus 1.6 times QK, which is 15. So you will get 54.8 kilonewton per meter. So this is 54.8 kilonewton per meter. So that is our ultimate design load. So design load per span. Design load per span. Design load per span design load per span is equal to, as you can see, our span is 8.5 from here to here, which is 8.5 meters. So design load per span will be 54.8 times 8, no, 54.8, then yes, times 8.5. So this one will be 465. 465.8 kilonewton. And this is our F. So F is equal to 465.8 kilonewton. Remember, we will use this F, this 465.8, in our proceeding calculation in the table provided in BS 8110. Now, after calculating the design load per span and the GK and the rest, what follows next is to calculate the ultimate design moment, which is M. And for this one, we will first check if this question will satisfy the condition provided in clause 3.4.3 of BS 8110. So we will now proceed to clause. Allow me to erase here. So we now proceed to design ultimate design moment. Ultimate. Which is M. So this one, we check if our question or our load satisfy the condition provided in table in clause 3.4.3 of BS 8110. So this clause states that the GK must be greater than QK. So our GK here is 22.0 kilonewton per meter, and our QK is 15 kilonewton per meter. Therefore, condition number 1, okay. We proceed to condition number 2. The load should be substantially uniformly distributed over 3 or more spans. So as you can see, we have more than 3 spans. So number 2 satisfy our the condition is okay. We proceed to the third one. Span are of equal length or variation. Yeah, span are of equal length or variation in span length should not exceed 15% of longest span. As you can see, our span have equal length, which is 8.5 meters, 8.5 meters, 8.5 meters. Therefore, all the 3 conditions are okay. Now you can proceed to a table which will give us the formula that we will use to calculate the ultimate moment. So I'm going to draw the table and later I will explain. Now, since our question satisfies the condition given in clause 3.4.3 in BS 8110, then it means we will use table 3.5 of BS 8110 to obtain ultimate design moment, which is M, and the shear force, which will help us to calculate the area of reinforcement of compression steel bars and the tension steel bars. So this is the table. I will show you the table. Then I will explain using the floor slab plan. So this is table 3.5 of BS 8110. As you can see, you can follow the movement of the cursor. You have the end support, end span, penultimate support, interior span, interior support, and then you have the moment and the shear. So since we are designing this beam, this T-beam, so it means support 3A, this is the support 3A, where the 3 and A are meeting. This is the support. So this is what we call end support. So it is the same support to this one on the far end on our right hand side. So these two are the end support, 3A and 3D. So the value that we will obtain for 3A will be the same value we will use for 3D. So we proceed to near middle of 3A and B. So near middle, which is the end span. From the end support, we proceed to end span. So from here to here, This is the end span. End span. Oronia Medru 3A and 3B. Like that. And then you proceed to support 3B. Support 3B is this one, where 3 and B are meeting. So this is the support 3B. Or we call it penultimate support. Penultimate support. Like that. Then we proceed to middle of BC, middle of 3BC, middle of 3BC here, or interior span. So this is the interior span. And remember, this penultimate, no, this span is equal to this one. It's the same as this one. This and this are the same. Also, this one, penultimate support 3B is the same as 3C. So the values we will obtain for 3B, we will also use it for 3C. Like that. So if you proceed to table 3.5 of BS 8110, that is the table. You can see end support. Our end support is 3A. Moment is 0. You can see here moment is 0 for the end support. Then we proceed to shear. So the shear is given by this formula, 0.45 F. Remember our F is we already have our F, which is 465.8. So you multiply 0.45 times 465.8, you will get 209.5. So that is shear and bending for support 3A. We proceed to near middle of 3A, B or end span. So let's check for bending. So bending, as you can see, that is the end span. No. That is the end span. Yeah, the end span, or near middle of 3A or B. So the end span is 0.09. You can see where my cursor is, 0.09 FL. So 0.09 FL, 0.09, and then F. We already have our F, and then L, the span distance, which is 8.5. You will get 356.3 kilonewton meter. And then you have the shear. So the shear, you can see the shear is, we have dash for the shear, which is 0. You will write here 0. We come to this support 3B. Support 3B, let's check for support 3B. That is penultimate support. As you can see, we have negative 0.11 FL. So negative 0.11 times F times L. F is 465.8, L is 8.5. If you carry out the operation, you will get 435.5 kilonewton meter. And then you have the shear for this one. So this one will be a bit tricky. I want to show you how you will go for shear. The first one will be 0.6 times F. Let me show you. We have the first here for the penultimate support, which is 0.6 F. 0.6 F. So this is 0.6 times F. We will get to 79.5 kilonewton. So this is support 3AB. So I will show you using a sketch. So as you can see, this is a continuous beam. A continuous beam, it means it's a beam which is resting on more than two supports. So we have support 3A. So this is support 3A. So this is support 3A. So this is support 3A. This is support 3A. And then you have 3B, 3B, 3B. This one, a half of this 3B. And then you have this one is again 3B. But here is C. So let's combine this one. So this one is C. So we will have 3BA, 3B, 3A, which will be the penultimate support, and then this one, 3B, 3C. So this is the interior. This 3B, 3B stroke 3C is the interior support. So this one will be given by, let's check for interior support. So the interior support is 0.55F. So this one is 0.55F, as you can see, 0.55F. Our F is 465.8. And if you carry out the operation, you will get 256.2 kilonewton. So we proceed. So after penultimate support, so this is the penultimate support, the next span will be interior span. So this is the interior span, or this one. This one is the interior span, or a middle of 3BC, 3B, then C, interior span. So the bending for interior span is given by the following formula, which is provided in table 3.5. So this is the interior, 0.7 FL. So 0.7, F is 465.8, L is 8.5. Then the shear force is 0. So you will get your answer to be 277.2 kilonewton meter as the bending. So I want to explain something. For a continuous beam like the one we are designing, the interior support will always have a negative bending moment. So as you can see, this one is negative 435.5. But when you will be designing, you will ignore this sign, negative, and use the positive value, which is 435.5. But when it comes to reinforcement, the negative means at the support, the reinforcement will be at the top of the beam, at that support, because the beam is hugging. The beam is hugging at the interior support of a continuous beam, which means the tension reinforcement will be at the top and the compression will be at the bottom. So I want to explain using a sketch, and I will clear here so that you can have more space for more calculation. So this is a continuous beam because it has how many support? 1, 2, 3, 4. So if I can draw this beam here, so that is the beam. So this is 8.5, 8.5, 8.5. So when this beam will experience bending, this is how it will bend. Here, there will be zero bending. Like that. So it means at the interior support, it is hogging. And this span, it is sagging. So for here is sagging, and also here sagging. Here is hogging, here is sagging. So for the interior support, M will always be negative, which means tension reinforcement will be provided at the top of interior support, and compression reinforcement at the bottom, like that. And where the beam is sagging, here the tension will be provided at the bottom and compression at the top. So that is the opposite. So that's why we have negative moment at interior support of this T beam. So let's continue. Since we have the ultimate design moment, we can now begin calculating steel reinforcement. So we will begin by support. We'll begin by middle of 3A, B, and 3C, B. So middle of 3A, B, and 3C, D. Or we have 3A. This one is middle of 3A, B, 3AB, and 3CD. So it means it is this one. This is the middle. Or we can just call them the end span. Let's call them end span. Like that. So we'll assume diameter of main bar is equal to 25 millimeter, and the diameter of the link is equal to 8 millimeter. Cover is equal to 30 millimeter. Then the effective depth. So the effective depth, which is D, is equal to H minus cover minus a half of diameter of the main link minus diameter of the link. So if I can draw this T-beam, so this is 37, 50, here is 150, and here is 400. So the H is equal to 150 plus 400, which is equal to 550 millimeter. And we have provided, okay, we have assumed a main bar diameter of 25 millimeter. So you can assume this is the main diameter, like that. So the cover, which is this distance, is 30 millimeter, and then the D will be this one, from the top to a half of the main bar. And also remember, we have the link. So you have the link. So it means D is equal to 550 minus cover, which is 30, minus main bar, half of main bar, which is 25 over 2, minus diameter of the link, which is 8. So this one is equal to 499. 499.5. So let's say it's 499. So that is our B. So since this end span, this one and this one, it doesn't have a reversal moment. A reversal moment, it means the ultimate design moment is negative. So which it therefore means the width of the beam will be lesser of the following. So the width of the beam will be lesser of the following. So the width of the beam will be lesser of, number one, the actual flange, which is equal to 3750 millimeter, and then B, web width plus LZ over 5. LZ is equal to 0.7 times center to center distance, which is 8.5. So this one is equal to, change this to millimeter, it will be 8500 is equal to 5950 millimeter. So therefore, web is the web width is 300. So 300 plus 5950 over 5 is equal to 1490 millimeter. So this one is critical. Now we'll use this one because it is lesser than the actual. So as you can see, this is lesser. So our beam, the width of the beam will be, so B will be 1490 millimeter. So K is equal to M over FC UB D square. So this one is equal to M. We already have our M, which is 356.3 times 10 raised power 6 all over FCU is 35 times 1490 times D is 499 square. So this one is equal to 0.0274. This moment, we already have it in our table. You can go back and check it. It is there. So it is in kilonewton meter. You multiply by 10 to power 6 to change it to Newton millimeter. So we proceed to Z. Z is equal to D 0.5 plus 0.25 minus K over 0.9 . So this one is equal to D 499 0.5 plus 0.25 minus K 0.02. So this one is equal to, Z is equal to 499 0.5 plus 0.25 minus 0.02. 274 over 0.9 square so you will get 485. Like that. So remember, Z must be less or equal to 0.95 D. So let's check. So 0.95 times D is 499. So this one is equal to 474. Therefore, Z, which is 487, is greater than 474 millimeter. Therefore, adapt 474 millimeter. Therefore, we proceed to X. X is equal to D minus Z over 0.45. So this one is equal to D is 474. No. D is 487. No, D is 499 minus 474 over 0.45. So this one is equal to 56 millimeter. So our X is 56 millimeter. So 56 millimeter is less than 150 millimeter thick slab. Thick slab or of flange thickness Therefore, hence, area of steel is equal to M over 0.87 Fy Z. So this one is equal to M is 356. We have this value in our table, times 3 times 10 to the power 6 all over 0.87 times 460 times 474. So we are multiplying by 10 to the power 6 to change from kilonewton meter to newton millimeter. So the area of steel is equal to 1878 millimeter square. So hence from the table provide 4y 25 area of steel is equal to 1960 millimeter square. I hope you know how to read this from the table. I think I have done it several times, so you can do it for yourself for practice. And then you can now draw the section for this span. this end span. You can draw the section for that. So this is the section. Remember, it's the T-beam. So provide 4y. Here the steel bar will be at the bottom. 2, 3, 4. Like that. So this is 4y 25. And the thickness of the slab is 150 millimeter, and here is 400. Millimeter, and here is 300. And then remember our D. Our D is 499. And the remaining distance is 51. So that is all about end span, this end span and this one. We now proceed to the support, the penultimate support, this one and this one. So this one and this one. So let's see how it will, let's see how the design will come out. Now at support 3B, at support 3B and 3C, or the penultimate support. Penultimate supports. So this is support 3B, this one, 3B, where 3 and B meet. And then 3C. Then 3C, this one and this one. So this one, you will assume the main steel, assume the main steel bar, the main steel diameter is equal to 25 millimeter. And it consists of 2 layers. Link, diameter of link is equal to 8 millimeter. Nominal cover, you have been providing the question, 30 millimeter. So the reason as to why we are assuming this, the diameters of the main bar and the link, is to help us to calculate the D, which is the effective length. So if I can draw this section, So remember, this is the interior support. These are the interior support. It means it will have negative moment. So negative moment means the main bar, which is the tension bar, will be at the top of this beam. So will be at the top of this beam, like that. Of course, we'll have another bar at the bottom, and then the link. Like that. So to calculate D, so this one is 25, and the link is 8 millimeter, and then you have a cover of 30. So forget about the bottom bar. So to calculate D, so D is equal to H minus cover minus diameter of main bar minus the link. So this is the D. So this is the D. So remember, our H is equal to 550. This is 150, thickness of slab. This is 400. So D is equal to H, which is 550, minus cover, which is 30, minus diameter of the link, which is 8, minus diameter of the main bar, which is 25. So this one is equal to 487 millimeter. 487 millimeter. So since the beam is hogging, at the support, therefore B is equal to 300 millimeter. So B is the thickness of the beam, like that. So remember this one, in the introduction to design of continuous L and B beam, we said that at the support of continuous member, due to the moment reversal is the negative moment which is experienced at the interior supports. So this is the negative moment. Therefore, B should be taken as the actual width of the beam. So where we have the negative moment, B should be taken as the actual actual width of the beam, which is 300. And like the other case, when the first reinforcement of this span, penultimate span you calculated, there were no a negative moment. So the B was the lesser of the two. So for this one, the B will be the width of the beam. So for this one, we will check for whether we will provide a compression reinforcement or not, because it has a negative moment. So to check, we first calculate mu, which is equal to 0.156 FCU BD square. So this one is equal to 0.156 FCU is 35, B is 300, and D is 487. So this one is equal to, remember to multiply by 10 raised power negative 6, so that you can have your answer in kilonewton meter. So this one is equal to 388.5 kilonewton meter. Now we compare with our M, the ultimate design moment, which we had from the table. So M was negative 435.5 kilonewton meter. So for this case, you will be ignoring this negative. Negative is just showing you where your main reinforcement will be placed. So you ignore the negative part and use a positive value. So this one, it means M is greater than mu. M is greater than mu. Therefore, provide reinforcement or provide compression reinforcement or a compression bars is needed. So for this one, we'll design for both tension and compression, because M is greater than mu. Now assume a diameter of compression steel. Assume a diameter of a compression steel to be 25 millimeter and the diameter of link to be 8 millimeter, cover 30 millimeter. Hence, D is equal to cover plus the link, the diameter of the link, plus a half of main bar. So this one is equal to 30 plus 8 plus 25 over 2. So D is equal to 51. millimeter. 51 millimeter. Then we go for Z. So Z is equal to D 0.5 plus 0.25 minus K over 0.9. 0.5. So Z is equal to D which is 47. 0.5 plus 0.25, K is equal to 0.156. So minus 0.156 over 0.9, 0.5. So Z is equal to 378. And Z must be less than or equal to 0.95D. 0.95 times 487 is equal to 463. So our Z is okay. Then, after calculating Z, we now proceed to X. So X is equal to D minus Z over 0.45. So this one is equal to D D is 487 minus 378 over 0.45, which is equal to 242. Is equal to 242 millimeter. So let's check whether the compression has yielded or not. So this one, it means D prime, this should be D prime, or the depth, the effective depth of the compression. So D prime over X must be less than 0.37. So 51 over 242 is equal to 0.21, which is less than 0.37. Therefore, the compression has yielded, i.e. Fs is equal to 0.87 Fy. We now proceed to the area of compression steel bars. So the area of compression steel bars is equal to M minus Mu over 0.87 Fy D minus D prime. So this one is equal to, our M is 435.5 minus 388.5. You multiply by 10 to power of 6. so that you can convert this one from kilonewton meter to Newton millimeter over 0.87 times 460 times B 487 minus 51, like that. So the area is equal to 269 millimeter square. So provide 2y25. Remember to maintain the diameter of the bar you assumed. So 2y25, the area of compression steel is equal to 982 millimeter square. And then we proceed to the area of tension steel bars. So this one is equal to mu over 0.87 FYZ plus area of compression bars. So this one is equal to mu is 388.5 times 10 to the power of 6. You change from kilonewton meter to Newton millimeter over 0.87 times 460 times 487, which is Z, plus area of compression steel bars. No, Z is 387. Z is 387. So times 378 plus the area of steel compression, which is 269. This is the area required and not the area provided. So you add the area required. So this one is equal to 28.37 millimeter square. Then from the table provide to y25, the area provided is no. Provide 6y25. The area provided is equal to 2950 millimeter square. Then we can draw our section. So this is our section. So we have the tension bar, which is 6y25. Remember, from the initial calculation of this, we assumed a two-layer of 25 millimeter diameter bar. So we will also maintain the same. So we have 6 So at the top, 1, 2, 3, 4. And then you are remaining with 2. 1, 2. So this is the tension bar. It is provided at the top because of the hogging. And then you have the compression bar, which is 2. So this is 1 and then 2. Then you have the link. Like that. So here, so this is 300 and this is 150 millimeter slab. The downstand is 400 millimeter. So this is 6. This bar are 6 in number Y 25. And this one are 2 Y 25. Then we calculate the D. So this is the D. This is 436. This is 51. And this is 63. Like that. Now we are at this juncture, at this point. Now we proceed to the final one, which is middle of 3BC. So 3BC, this part, or the interior span. So middle of 3B or interior span. So assume a diameter of main steel to be 25 millimeter and the diameter of link 8 millimeter, C 30 millimeter. So D is equal to H minus C minus main bar over 2 minus diameter of the link. So this one is equal to 530 minus 30 minus 25 over 2 minus 8. So this one is equal to 499. The same case to the first for the first span. So D is equal to 499. And then the effective depth of the beam is lesser. No, effective width, not depth. Is lesser of A, the actual flange, which is 3750 millimeter, B, web width plus LZ over 5, and LZ is equal to 0.7 times 8500. So this one is equal to 5950 millimeter. So this one is equal to 300, which is the web width, plus 5950 all over 5. So this one is equal to 1490 millimeters. So this one is the critical. It remains the same for the first span, or for the end span we calculated earlier in this question. So area of steel is equal to M over 0.87 Fy. So this one is equal to 277. This M is, we already have this M in our table, in our initial table, 277.2 times 10 to the power 6. You change it from kilonewton meter to Newton millimeter over 0.87 times 460. This should be Z times 0.95 times 499. So remember, in our first calculation of the area of steel in this span, the end span, Z was less than 0.95 D. So we decided to go with 0.95 D. So the same case will imply here. So area of steel, which imply area of steel is equal to 1461 millimeter square. Then we'll say provide 3y25. Area of steel is equal to 1470 millimeter square. So the way we have done this is the same way we did to the first end span. So procedure is the same because they have positive moment. But for this middle support, it is different because of the hogging part of it. And then you can draw the section. So this will be the section. So you have three number, 1, 2, 3. We can have the hanger bar at the top. Like that. So this is 3y 25. These are the hanger bars. So we end there for today, but we have not done with this question. So next time I will design for shear. So this question we were to design for bending, shear, and then we check for deflection. So because it's a very long question, we can't do it the whole of it today. So I'm remaining with the shear part and the deflection. So in my next session, I will continue with shear and then we check for deflection. But for today, we end there. So subscribe to my channel if you haven't, and hit the notification bell to be notified when I upload a video. Thank you for your time, and we meet again in my next session.